All right, so today we're going to finish with some projectile motion, do some circular motion, and hopefully get a good way through some Newton's laws. But before I actually write anything down today, I want to show a little video. This is maybe one of the demonstrations I would have done in person. Let me drag the window over. So this is a demonstration from Harvard Natural Sciences. And let me go like this. I've slowed the video down to maybe make it more clear through the recording or this Zoom call. So on one side of this device, there is this yellow ball that will fall directly downward. And on the other side of the device, there's a ball that will be sort of launched. You think of it like a ball rolled off of a table. So they're both initially at the same height, but one of them is going to fall downward, and at the same exact time, the other one's going to be pushed and launched, from this other side, and will fall downward also. So why I'm beginning with this video is because I want to show that it is as simple as I was saying last time. You could break all projectile motion, in all motion really, into its very simple component forms. So in this case, this is a demonstration to show that even though something is moving, it has some sort of movement in a horizontal direction, it is still going to be accelerating downward at the same rate. So let me play the video. You'll see that as they are both released, hopefully it's clear through the Zoom call that they both hit the ground at the same time. So one more time. And it's almost, you can see at each step, the video has slowed it down with the frames. At each time interval, maybe I can't go frame by frame. So this, breaking up of just the vertical component, just the horizontal component, that is something I'm going to start with in my notes. So let me bring up where we're going to start. So I'm going to have this graph. It's going to be similar to, it's not a graph, it's just sort of a diagram of kind of that same experiment. We have a ball that is, think of it just rolling off of a table. So at some point it is moving horizontally, and then right as it reaches the edge, let me zoom in. Right as it reaches the edge, and right as it reaches the edge, it will begin to start falling downward. However, it still contains its horizontal velocity. So we can break this up into sort of, individual moments of time. So a good measure is to just measure, equal time intervals. So after, I don't know, I'm just, assigning a value, I'll say a quarter of a second, the ball is here along the path. After another quarter of a second, the ball would appear here. And After another quarter second, the ball's here, and you can see another quarter second, it would be at the bottom. So this is me sort of slicing this path up into equal intervals. And hopefully you've seen that in this video, or you notice that we can just look at the vertical component. The ball that was falling straight down did exactly the same thing, or reached the ground at the same time as the one that was being propelled. So let me sort of, this is just going to be like a kind of I'll hopefully make this clear. I'm only looking at the vertical components. So I've sort of connected a line to the center of that ball, of the ball at that slice of time. So the origin, the ball was up here, and after one slice of time, it didn't move down nearly at all. It was right here. After another slice of time, these are equal slices, the ball was right here. After another slice of time, the ball is here. And after another equal slice of time, the ball is here. This sort of, I'm sure you've seen these pictures before. Someone will take a, photograph and will like frame all of the images of the motion on one picture. So what this is showing is that after, 1 moment, it's moving a little bit. After another moment, moving a little quicker, then moving a little quicker, and finally moving, very quick. It's speeding up is what we're noticing. I can also point out that I can slice this, or I can just look at the horizontal components. So let's slice it. Again, these are equal time intervals. So we have the ball right when it started, or let me make this a bit clearer before I move on. This is the vertical only. And that's my other thing. I need to change color. So I'm going to this is the vertical only. I'm only looking at the vertical, components of this path. So now let's look at the ball when it's moving this trajectory. Let's look at just the horizontal components. Well, at one time, I'm going to follow this straight down. The ball is right here. After one slice of time, the ball is right here. After another equal slice of time, the ball is here. After another equal slice of time, the ball is here. So maybe we can see with this, diagram that I drew, I'm just doing this by hand. This is true in nature, is that if something is moving in a horizontal direction and it's not accelerating, it will continue to move at that velocity. So let me show that there is, after one slice of time, it moves with that velocity, it moves with that velocity. So the velocity is not changing over time. So I can say horizontal only. And I can sort of, claim that there is a constant velocity here. And for that vertical component, there was a change in velocity. We saw at equal time slices, the ball is moving quicker and quicker. So there is a change in velocity. Okay. Let's move on. Let me try to keep that in frame still. Let's move on to a little example, and then we're pretty much done with projectiles. So an example that goes over, kind of this subject, or I guess, similar to what I've done above, is think of like a firefighting airplane. It's trying to drop, a tank of water on a burning forest. So the pilot will maintain an altitude of 100 meters, and the plane is traveling at 800 kilometers per hour. What we want to know is, at what horizontal distance in front of the fire should the pilot release the tank of water? And of course, we could assume no air friction. So let me go down here to the problem. And a way I like to always start is with picture. It helps me, see what is happening in my head. I like visuals. So we have a plane that is flying very quickly towards a fire, and it's also very low. So it needs to judge how far the water is going to move while falling. So let's put in the details that we know of this problem. So we know that the plane is traveling at 800 kilometers per hour. We know that the plane is maintaining a constant altitude of 100 meters. And what else do we want to, we want to know at what distance in front of the fire should the pilots release the water? Okay, let's start out with, there's another value that we can say we know. We know that's the acceleration due to gravity, g, is 9.8 meters per second squared. Is, assuming we're on Earth, we can use this value for g. Now let's go over sort of how we're going to approach this problem. First off, I noticed that the units are different. So this one over here is a unit of meters. This unit right here, it's kilometers per hour. And this one right here, the units involved are meters per second squared. So we need to, before we even begin, finding the right equation, putting in values, we need to make sure that our units will mesh clearly together. So we need to make sure that they all are the same. Whatever we're going to agree on starting with. The problem doesn't say I need the answer in kilometers or I need the answer in meters. So what I'm going to do is, this is meters per second squared. I think it's easier for me to convert this value, 800 kilometers per hour. let's convert that to meters per second before we start the problem. So it's a 800 kilometers per hour, or let's go a bit more clear. It's 800 kilometers in 1 hour. And we want to get to meters per second. So we need to have meters on the top. So there are 1,000 meters in 1 kilometer. We see that will cancel out the kilometers, leave meters on the top. And we want hours. We don't want hours, we want seconds on the denominator. So we will have, what was it? It was 3,600 seconds in 1 hour. So we should be getting a value of, about 222 meters per second. That's how quick the plane is flying. All right, so now we can begin the problem. Okay, I'll just sort of underline that. We want to know, first off, the water, I put a dot up here. So the water is released right here, and it's going to, again, like that example I have up at the top, it's going to leave, it's going to make an arc like this. So it's going to have some horizontal component and some vertical component. We need to separate them. So to start out, we can find just the vertical component. So let's say just the vertical component of a kinematic equation to use. Let's use this one. Delta y is equal to the initial velocity in the vertical direction minus 1/2 g t squared. Okay, so it's minus because we're going to say that's, I guess that's a good point, is we need to also label what is positive and negative on our little diagram here. So let me, instead of writing 100 right here, I'm going to put 0 up at the top where the plane is. I'm going to say the water will fall down here 100 meters. So that will be minus 100 meters. So I'm going to say down is negative. So I'm going to say, or I could just label, the whole diagram. I could say up is positive and to the right is positive. Okay. So we have this kinematic equation here. What does the vertical initial velocity equal? So right when it starts, right here, this is the same as the ball rolling off of the table. So right when it leaves the surface of the table, it's not moving down, up or down at all. It's only moving horizontally. So, oh, sorry, there should be a T in here also. So, since there is no initial vertical velocity, that value goes to 0. That whole, term goes to 0. That makes this problem a lot easier. We'll say delta y is equal to minus 1/2 gt squared. What are we trying to solve here, though? We know how far the water is going to fall. and we know the acceleration of gravity. What I'm trying to get is I want to know how long it takes for the water to reach the ground. So I'm going to be solving for t. So before I put any values in here, let's actually just rearrange this to solve for t right now. So I'll say this is the same as t equals, so if I multiply the 2 over here, I'd have to then divide the g over. We'd end up with something like this, minus 2 delta y over g. And you might look concerned about this negative sign inside of the square roots, but remember, we're starting at 0 and we're falling 100 meters. Or, let's see. We could either arrange it like this, or I think I had it the way I preferred at the beginning. Let's call, the origin right here is 0. And up here, the plane is flying at 100 meters. It's going to give me the same result. It's just this, I think, is a bit more clear to see. So we have minus 2. The final height, which is 0, minus the initial height, which was 100 meters. That's where you can see there's this negative 100 appearing. And g, that's 9.8 meters per second squared. And all of this is under square root. And I'll just say underneath, I'm not going to do any more intermediate steps. I'll just say t, the amount of time it takes for the water to go from the plane to the ground is 4.5 seconds. That's really, helpful, but the problem didn't ask for the time. The problem asked for the distance in front of the fire. So that's where we've split up the 2 coordinates and we've solved for, time using the vertical component. And we can use that same time and plug it into the horizontal. So I'll do that over here. So we have delta x is equal to the initial velocity in the horizontal direction times time plus 1/2 ax times t squared. So the pilot is maintaining the same speed. They are not accelerating, speeding up or slowing down at all. So that means there's no acceleration term. So this whole thing goes to 0. Also, remember that as things are falling, we're assuming no air friction. So as the water is falling, it won't be accelerating in the horizontal direction. So that's primarily why this is going to 0. The initial velocity right here is this 222 meters per second. So delta x equals v naught x times t. And that is where you can hopefully see that we're going to plug this value we found for the time into this equation. Equals, let's just meters per second times 4.5 seconds. We get a result of, delta x. That's just, final minus initial, or, this range. We get a result of 999 meters. So just about, I could pretty much round this to 1 kilometer in front of the fire. This pilot has to release the tank of water. So if they're fighting a fire, it's going to be urgent, and that'll be a waste of resources if they miss. All right. So there is a little example on that, and we're going to move on to circular motion. I'm not going to go too much into circular motion. Later on, we're going to have a chapter on rotation and angular momentum. So we're just going to, graze the surface with some circular motion right now. Okay. Circular motion. Okay, so let's say something is going to move in a circular path, like a ball on a string. You're swinging around, or you think of just as a particle in space. However you want to think about it, we're just going to look at how this thing is moving. So there's our ball. It's going to be moving in some direction. If I was to take a picture of a ball moving along a circle, circular path, if I was to take a picture of it, right at that moment, right in the picture, it's going to be moving straight up for that split second. If I was to then take another split second picture, after the ball's traveled a bit, now the ball or this particle appears to be moving, completely a different direction. Now it's angled to the left. After another split second, the ball can appear up here. You see, these are these tangent velocities that are, or these are these velocities that are tangent to this, circular path. Let me, add a couple more in here as time goes on, and I'm only going to do that many. We can see that this object, it's a ball on a string or a particle, just moving in a circle. It's changing its direction. And previously I was talking about how we can take something's horizontal components and something's vertical components, and we could sort of split them up and only look at those two things separately. So we can do that also with something moving in a circular path. So let's take these components of this thing moving in a circle. Let me zoom in a bit. So for a moment, that first moment, I'm not going to give any values or anything. I'm just sort of label generally. For a moment, there is a positive velocity in the y direction, and the velocity in the x direction is 0. And after a moment, now the components are, now there's a bit of a negative velocity in the x direction, but still a positive velocity in the y direction. After another, brief moment, now there's no y velocity anymore. There's no vertical velocity anymore at the top of this circular path. But there is a negative horizontal velocity. It's moving completely to the left. After another, split seconds, now there's a negative horizontal and a negative vertical direct velocity. And finally, on the other side of this circular path, there is a no more horizontal velocity, and there is a negative vertical velocity. So this thing is constantly changing direction. It's constantly, remember when the velocity changes, that's an acceleration. So it's constantly accelerating as it moves around the path of a circle. So because it's continuously changing its direction. So since it's, if this thing was to go forever, it's going to be constantly forever changing its direction. It's constantly accelerating, experiencing an acceleration. So what is it? What is this acceleration? Like, how do I, wrap my head around it? Maybe I can, do some calculations with it, predict something. This is going to be called the centripetal acceleration. And it's going to always be pointing towards the center of some circular motion. So in this case, all of these arrows are pointing inwards towards the center of the circle, or the point of rotation. So all of these values, all of these, vectors, see, these are all the centripetal acceleration. It's all the same value, and it's all pointing towards the center of this circular motion. And that's how to that's how we are able to classify this acceleration that's always changing. It's the same value, but it's always going to be pointing towards the center of rotation. And let me, so centripetal. There's the way I see it is you just look at, it says trip in the middle. So that's center seeking. I guess I could put that center seeking. Okay, let's do a little, example, or not necessarily an example, another diagram of like a pendulum on a string, some mass on a string. Think of like you're swinging a yo-yo back and forth, or whatever you have. At one end of a swing, where this blue dot is on the left, we could say, this object, whatever it is, it has no velocity. It's at the highest point. So up here at the top, it has no velocity. I'm just going to say 0. So that's on the left side. And assuming this is, frictionless, environment, it's perfect and everything. Also, at the other side, it's at an equal height. It is also 0. The velocity is also 0 because it will swing all the way through and reach a point where it stops. Why does something on a pendulum or a swing set, why does it stop at one side of the swing? And this is where we're going to have to not only add, X and Y components from, a coordinate system, we also have to think about adding separate vectors of acceleration together. So the blue represents a velocity. Let me introduce, some acceleration vectors. So I put those in red right here. Let me match the color. So on the top, all of these ones pointing towards the center of the path, remember that is the centripetal acceleration vector. It's pointed inward towards the center of the point of rotation. And that's a messy arrow, so it's like that. Okay. These are vectors. The ones on the bottom, those are from gravity. That's always going to be pulling down. Think on a swing set, every point on your swing, gravity is pulling or trying to make you accelerate downward. It's accelerating you downward like this. So this is the acceleration from gravity. Acceleration due to gravity like this. And like this. Like this. And you notice they're all the same, general size. Same magnitude. It's because gravity is just about the same everywhere on Earth. Okay, so we have these two red vectors that I've added to this diagram. Now we would have to sum these red vectors that I've put on this picture. So I've made just sort of a crude picture, summing the vectors together. Before I draw them, maybe you can guess where they're going to appear. So on looking at this set over here, this one's pointing down, this one's pointing to the right. So we have, summing these two vectors together, we're going to expect something that looks like this. And for the next set right here, we have, they're becoming almost opposite each other. They're not quite canceling each other out, but it's, whereas up here, there's a lot downward, a lot of acceleration downward, pointed downward like that. For this case, they're going to cancel each other out mostly, but then there's a little bit still accelerating it to the right. Then you see at the very bottom, these two vectors are just going to cancel each other out. And there's no acceleration at all once it reaches the bottom. When it gets to the other side of the path, then it reverses. There's a little bit pointed backwards like this. So the swing starts to slow down once you pass through the other side. It's accelerating you back the other way, opposite to your velocity. And finally, at the very top, it's accelerating you, it's a large vector back down like this. So I'm going to, I just introduce just some pictures of that. And let's see. I'm not going to go through any derivations to find this centripetal acceleration. What I'm going to do is just follow a little, like with most things with this circular motion, I'm just going to try to show with a little diagram. Maybe make it at least somewhat make sense before I write an equation down. So we have a particle that's up here, that is moving with some velocity at a given time. So I look at my watch and I see, oh, right at this time it's moving at that velocity. And at some later time, it will be over here. So the particle will appear over here, and it will be, whatever time I looked at it the first time, plus, a little change in time. So this is me, tracking where it is, what's its velocity as time changes. And this is related to this object's moving in a circular path. So it's always the same distance away from the center, or, think of like the pivot point, which initially was this, some sort of, distance away, at a given time. But maybe actually, in fact, what if it's not, constant, distance away? Well, if we just want to make sure, just in case it's, not a perfect circle. Well, I could say that over here, just to make sure I include all, all options, I'll say now it's at some radius, whatever at another time, wherever it was to begin with, and then plus a little bit extra, probably. So whatever that value is. And as we've done before, we could get this position vector. And this is where I'm going to skip like a lot of derivation that I'm just going to write down using sort of geometry. And you see there's this change in velocity, this change in these coordinates. We can get a sort of ratio between how fast it's moving versus how far away it is from this center of rotation. So we will get centripetal acceleration is just the equation C equals the velocity squared over R. And I believe that's a vector. Let me check. I don't think so. Okay. So we can leave it just like this. We can also, if this thing is moving in a circular path or anything of the like, we can find how long it takes to complete one complete path around this uniform circle. So this will be the period, which is commonly labeled as T. So it's just a timing of how long does it take for this object to complete one thing, one revolution. So T equals 2 pi times the radius of this motion, over the velocity. So how quick is it moving? And finally, this one should be, I believe we've already sort of covered this. I'm just including it here. Tangential acceleration. That, of course, is, we'll just say a t, is, that infinite slice of velocity. And we're looking at these things right here. So what is the, at that very instant, what is its acceleration in, a tangential slice? So we have to look at the very small slice of velocity over a very small slice of time. Okay. There's that. We're going to do a little example with circular motion before we move on. So we have a satellite. It's going to be moving at a constant speed around Earth. And we want to find out. So a satellite moves at a constant speed in a circular orbit around the Earth. And we're going to actually assume that it's, it's near the Earth's surface. So we're going to assume in this problem that the Earth is exactly, 6,370 kilometers. And we could say that the satellite is about that distance as well. So since there's no other value for a radius, that's what we're going to be using as a radius. If the magnitude of its acceleration is g equals 9.81 meters per second squared, we want to find its speed and the time it takes to complete one revolution. All right. Like always, I start out with a picture. And I clearly label what's happening. So the satellite is moving. At this briefest moment, it's moving directly that way. But it's also being accelerated downward towards the center of the Earth. Like that. The equation for centripetal acceleration was this. And we also are given that the magnitude of its acceleration is just gravity, the acceleration of gravity. So what this is saying, what I've just underlined, is saying that this centripetal acceleration is the same as g. So we could say that, g equals v squared over r, like that. We want to find its speed. So we want to find its speed. So pretty simple. We're just going to solve for the velocity in this equation. The velocity, we would have to multiply the radius over and square root. So it'd be g times r under a square root. And I'll just quickly put in some values here. Something else that I should note is that this value for the radius is in kilometers. It would probably be easier. So let's make that meters, since g is in meters per second squared. And we can't mix something with meters and kilometers. They both have to be the same unit. So let's choose meters is something we're going to convert it to. So we're going to say g, that was 9.8 meters per second squared. And the radius in meters is 6370 kilometers. So that's times 1,000. So 1, 2, 3, 1, 2, 3 meters, like that. All right. So our value is a velocity of 7,905 meters per second. Oh, I'm sorry, there was a 1 here on how we're going to take gravity. So 9.81 meters per second squared. And since there are 3 significant figures in that one, there are also 3 significant figures in that one, it wouldn't hurt to make the answer that we have at the bottom also 3 significant figures. So at the third place, we're going to round. We're going to round whatever is on the other side. So 7,910 meters per second. All right. Next up is the period of the satellite. See if I could fit it on the page at the bottom. So we have the period is 2 pi r over the velocity. And at this point, we know all the values, and we also have just found the velocity. So it should be straightforward and just sort of putting these into a calculator. 7, 0, 1, 2, 3 meters over and just doing this we will end up with 5,059 seconds. If we wanted it in minutes, I could just say this is about 84 minutes. It takes 84 minutes for the satellite to go around the Earth once. So, a little over an hour. Okay. All right. So we've basically finished chapter 3 today. Yeah, so this is chapter 3. And we're going to be starting Newton's laws. So let me, it's just sort of a big introduction into Newton's laws. I have a couple statements. Not until the very end where I have maybe an example if we get that far today. But we'll see. So let's introduce some Newton's laws. Chapter 4, yeah. Okay, and I'm going to go quick over these. So if you don't get a chance to write it all down, you could just check out the notes later or the video later. So now that we have looked at several ways of how things move, this is where we ask the big question of like, why do things move the way they do? We're able to describe an object that falls. We could predict where something can be the trajectory of a projectile. We can predict where something will be along a circular path. We know all about velocity, and a change in velocity is an acceleration. But what causes all of these changes? What we want to know is how and why. And that's where Isaac Newton, Sir Isaac Newton, he refined the way we think about motion, from its like very core. In the 1700s, Isaac Newton was sort of in quarantine. I think there was a plague of London that everyone was in quarantine. They're just spending a lot of time at home. And while at home, Isaac Newton, he discovered or developed a whole system of motion and some forces that we'll go over in a minute. So he developed his own sort of notation for this branch of physics. He also, in order to do this, he also invented calculus while at his home, stuck at home in quarantine. So inventing calculus, he's like, how do I get these things to be, I have to add up infinitely small segments of an object to describe how something moves. How can I do that? And so he had to invent pretty much the common way of how we do calculus. So for a lot of this sort of reasoning I'll go through, he was maybe not using calculus for it. He was doing a big sheet of paper with line graphs, mapping out and measuring and drawing another line and measuring. So very laborious. He got tired of that and he wanted to speed it up a bit. So let's go over Newton's first law, something that he sort of said, this is something I've seen and measured and observed everywhere. This is something I'm going to say is a law of nature. Newton's first law says that an object at rest stays at rest unless it is acted on by an external force. He also noted with this statement that an object in motion continues to move or continues to travel with a constant speed in a straight line unless acted on by an external force. This is often called Newton's Newton's first law, or I could just say law of inertia. Maybe you've heard the term inertia around somewhere. That's just sort of, something's physical properties of, does it resist moving? Does it sort of stay still? Something that helps me when thinking about Newton's first law is think of your like an astronaut in space, and there's nothing affecting anything. You're just in empty space, not even gravity around you, and you give an object, a stationary object, you look at it, you wave your hands around it, it's not going to move. It's going to stay at rest. An object at rest stays at rest. Once you give it a push, once you give it a push, it will continue to move with that constant speed in a straight line forever, unless it's acted on by an external force. If you don't like, if that's too big of a leap, you think of like an air hockey table. If you leave the puck still on an air hockey table, it's probably going to stay still. But if you give it a tiny little tap, the puck will start to slide at a constant speed. That's a real life kind of example. So in order for Newton to make sense of this thing he's declaring, his first law, he has to develop a proper frame of reference. If I give something a push and I am also moving, how am I going to describe this? How am I going to declare a law around something when there's a lot of factors going on? So that's where Newton needed to develop, and at least needed to clarify, what he's calling an inertial reference frame. So an inertial reference frame is something that is traveling at a constant velocity. So again, say I'm an astronaut in space. I am holding my water bottle, and nothing around, nothing affecting anything. And I give it a push, I can see it's moving away slowly. But let's say I myself am moving very quick through space. I can see like stars moving around me. I'm moving incredibly fast. I can also, since my own inertial reference frame is constant, I'm not being accelerated. This is an inertial reference frame. I can also give the water bottle a little push, and I'll see it move away slowly from me. And I, myself, am the inertial reference frame. So I just see it moving, pretty slow, even though in the grand scheme of things, me and the water bottle are moving very quick. The sort of real world example of this is, let's zoom in on this. So imagine like a school bus full of kids, and while a kid, on a way to like a soccer match or something, inside of the school bus, a kid is able to, hold on to a soccer ball, and it doesn't look like the soccer ball is moving, even though the bus itself is moving at a constant speed. And inside of the school bus, the whole inside of the school bus is an inertial reference frame. I'm gonna just delete all of that. Maybe I'll shade it in a minute. Since the whole inside of the school bus is an inertial reference frame, the kids are able to toss up the ball, and the ball doesn't immediately like accelerate backward past their shoulder. even though they're all within the school bus. Hopefully you can see sort of the two sides of thinking and maybe the need of at least stating this, that some things that are already moving, we just declare that this zone is the inertial reference frame. So everything within it is going to obey Newton's first law. Okay. Next up is what can we define? Something's not going to move unless it's acted upon by a force. Well, we also need to define what a force is. So we can define a force as an external influence or action that causes an object to change its velocity. And I just put a little reminder right here that changing your velocity is an acceleration. With respect to the inertial reference frame. So just think of everything as all a part of the same reference frame. A force is something that will act upon another object, making it change its velocity. So there are what are called contact forces, and it's not called non-contact forces, it's called action at a distance forces. These can be sort of labeled as, there are four big ones, or I guess there were. They are, currently in the works of maybe combining some of these on sort of the research level, physics. There is the gravitational interaction. So, how do particles of mass interact with one another? Actually, before I think I glazed over a little too much. Contact forces, those are the ones that we will all know, sort of like a push, pull, hit, throw. All of those forces that we all sort of intuitively understand already. So those are contact forces. When one object is in physical touch of another object, causing it to change its velocity. The action at a distance forces can also change something's velocity just without physically getting near one another. So there are the gravitational interaction. I'll just say attraction from mass. I'm just going to, very, simplify all of these. You don't have to write all of these down. Say mass. Second one, electromagnetic interaction. That's things of charged nature. Attraction. I'll just say attraction from charge. The weak interaction. That's something that actually forms the things that make atoms themselves. So think of an atom, one of the smallest things possible. What is it made out of? It's made out of protons, neutrons, and electrons. But in recent developments, I believe since the 80s or 90s, we've noticed that each of these things are also made out of smaller components. They're called quarks. So the very, very much smaller than these individual things themselves are, being held together. They're being formed by something. That's called this weak interaction. So I'm just going to say keeps quarks together. And the strong interaction, that is the thing that keeps all of the atoms themselves together. You think of how do, in an atom of, helium, there's two protons. They're both positively charged. And you'll learn later on that positive charges repel one another. Why are they, still clinging to each other on the inside of a nucleus? And that is from this strong interaction. So this keeps atoms themselves together. Keeps atoms together. So these are just, this is just the side notes on these 4 fundamental forces of nature. I think I can get through this. Let me zoom out. We'll go through. Forces are going to be seen as just like vectors. You can have a force pointing in one direction, you have a force pointing in another direction, and you can just sum them together just like vectors we've already done before. And the total force, we can say the net force, is just a sum of each individual force. So remember, these are vectors, so they'll have their, horizontal components and their vertical components. You have to go step by step for each of these. So forces are, fairly easy once you can get the hang of them. And finally, we want to talk about mass. So an object, I just sort of assumed at the beginning that an object is made of mass, and I just sort of told you guys that at the beginning of the semester. But what is mass? Well, an object's mass is related to an object's inertia. So how does an object sort of resist change? So inertia is something's ability to resist change. For mass specifically, let me zoom in a bit. For mass specifically, it is how likely an object is to resist motion. So more mass equals more inertia, which means there's a bigger resistance to motion. And I guess I put the SI unit for mass is 1 kilogram. SI units for mass is kilogram. Okay, and yeah, I think I have to stop right here because I'm out of time. I have one more page, and we could go over this. We could start right here tomorrow. All right, so yeah, so we're beginning chapter 4. I should be able to finish this by the end of the week, chapter 4. And next Monday will be the quiz on chapter 3 and 4. So, like projectiles and motion in 2 and 3 dimensions from chapter 3. And we're pretty much going over all of Newton's laws in chapter 4. All right, so with that, if you guys have any questions, you can ask me now, or you can always email me. Otherwise, I'll see you guys later.